Ray optics. In this chapter, let us confine to refraction and a total internal reflection. What is refraction? And explain Snell's law, total internal reflection, optic fiber, uses of optic fiber, lenses, and refraction in lenses. These are the concepts which I am going to discuss. While discussing about refraction and then Snell's law, let us consider two media. The one above the line is medium of refractive index mu1. The other one is the below the line is second medium of refractive index mu2. And theta 1 is angle of incidence, theta 2 angle of refraction. Snell's law states that sin theta 1 by sin theta 2 is a constant. Sin of angle of incidence to sin of angle of refraction is a constant. This is Snell's law. From this we define this constant is taken as refractive index. This constant is taken as refractive index and it is indicated with mu 12. Mu 12 refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium. It is given by mu2 by mu1. Snell's law is also written in the form mu1 sin theta 1 is equal to mu2 sin theta 2. Mu1 sin theta 1 is equal to mu2 sin theta 2. Now we will pass on to the concept. When a light ray passes through different media, it bends at the interface of the two media. That is called refraction. Let us take the case in which the refractive index of the first medium, mu1, is less than the refractive index of the second medium. The refractive index of first medium, mu1, is less than the refractive index of second medium. Then we notice that the angle of incidence theta 1 is greater than the angle of refraction theta 2. So if a ray travels from rarer medium to denser medium, it bends towards the normal. Let us take the other case. The ray bends away from the normal if mu1 is greater than mu2. If the refractive index of the first medium is greater than the refractive index of the second medium, then the angle of refraction theta 2 is greater than the angle of incidence theta 1. Theta 1 will be less than theta 2 when the light ray enters into rarer medium from denser medium. If the refractive indices of the two mediums are equal, then theta 1 will be equal to theta 2 and the ray travels undeviated. The ray travels undeviated if mu1 is equal to mu. Total internal reflection. To understand and to study total internal reflection, let us consider a denser medium like glass. Inside the medium, let us consider different rays incident at the point O. Let PO, QO, SO be different rays, different paths traversed by different rays, and they are all incident at O. We know that a light ray which travels from denser medium to rarer medium, it bends away from the normal. So the ray PO, after emerging into air, it makes more angle with the normal. It bends away from the normal. So for a particular angle of incidence, the ray should pass along the surface of separation. Let us consider QOB such ray. QOB, the ray for which the emergent ray travels along the surface of separation. So the angle of emergence is 90 degrees. Now the angle made by QO with the normal, let us call it as C, known as critical angle. This angle for which the angle of emergence is 90 degrees is known as critical angle. The ray SO is making an angle greater than this critical angle. SO is making an angle greater than C, greater than critical angle. Then it will travel into the denser medium after reflection at the surface of separation. So a ray which is incident at an angle greater than critical angle C, it will be reflected back into the denser medium. Such a reflection is known as total internal reflection. Total internal reflection. So total internal reflection takes place when a light ray traveling in a denser medium, if it is incident at an angle greater than critical angle at the surface of the two media, then it undergoes total internal reflection. If C is critical angle, then that is the angle of emergence for this angle is 90 degrees. So mu is defined as sine of angle of incidence to sine of angle of refraction. Generally we take the angle of incidence as the angle in the rarer medium and angle of refraction as the angle in the denser medium. Hence we will get mu is equal to sine 90 by sine C. So mu is equal to 1 by sine C. Optic fiber. Optic fiber. It is a thin wire through which light signals will be passed. It works on the principle of total internal reflection. It works on the principle of total internal reflection. The total internal reflection occurs at the interface of core and cladding. The total internal reflection occurs at the interface of core and cladding. Let us see how this optical fiber is situated. Optical fiber, structure of optical fiber. Let us look into the figure. Here mu2 represents the core, the central part of this fiber. The central part core having a refractive index mu2, and it is surrounded by a medium of refractive index mu1 which is less than that of mu2. Core with a greater refractive index with refractive index mu2 is surrounded by a medium of refractive index mu1 which is slightly less than mu2. It is called cladding. This cladding is surrounded by another structure known as supporting structure, a hard material. So this is how the optical fiber is structured. It consists of three layers: core, cladding and supporting structure. Core will be at the center and cladding will be sandwiched between supporting structure and core. A light ray entering at an angle of incidence I, a light ray incident at an angle I known as launching angle, gets refracted into the core. Since the refractive index of core is large, it gets refracted towards the normal and travels in the core, and it is incident at the surface of separation of core and cladding. At the surface of separation of core and cladding, it is incident and it undergoes total internal reflection. The angle of launching is such that the angle of incidence at the cladding, core cladding interface is greater than critical angle. So it undergoes total internal reflection. It gets reflected once again and it is incident at the second surface, and once again the angle of incidence will be greater than critical angle. Like this, it continues to travel inside the core by undergoing multiple reflections in the core. It will always be incident at an angle greater than critical angle on the core cladding interface. So it will not come out of this structure. It continues to travel in the same structure. The launching angle, minimum launching angle I, is given by the relation sin I is equal to square root of mu2 square minus mu1 square. Using this relation, we can determine the launching angle. The uses and advantages of optical fiber. The uses and advantages of optical fiber. Now we are using coaxial cables. The information carried by a single optical fiber is much more than the information carried by 1500 coaxial cables. A single optical fiber can carry as much information as carried by 1500 coaxial cables. So it carries more information. Now the coaxial cables, the communication is interrupted by lightning and external electromagnetic radiation. The communication through coaxial cables, it is disrupted by lightning and external electromagnetic radiation. But external electromagnetic radiation will have no effect on the communication of optical fibers, because the communication is different, it is light, hence it cannot be disrupted. Speed of communication is highest because here we use light, which has got the highest speed. Since light is the communicating medium, it has got the highest speed, hence the communication speed will be very high. Optical fibers are used in laparoscope and endoscope, which are the instruments used in the examination of innermost parts of human body. Optical fibers are used as sensors in industry to measure temperature and pressure. Optical fibers are used in sensors in industry to measure temperature and pressure. These are very light in weight, flexible, they can be bent in any direction, and they are very cheap. The optical fiber is a very thin wire, so the size of the cable is very thin. Now our aim is to study about the nature of lenses. First, what is a lens? A lens is made of a transparent medium bounded by spherical or plane surfaces. Lens is made of a transparent medium like glass, and it is bounded by a spherical surface or both spherical surfaces, or a spherical surface and a plane surface. For example, a double convex lens, both the surfaces are convex. A double concave lens, both the surfaces are concave surfaces. A plano-convex lens, one surface is convex, other one is plane. Plano-concave surface, one surface is plane and the other is concave. Like this, we can devise several lenses of different shapes. Now we define certain parameters, certain properties of the lenses. One is principal axis. Let us take a double convex lens. The line passing through the centers of the two curved surfaces. The line passing through the centers of the two curved surfaces is called principal axis. This will pass through the center of the lens, known as optic center. Then the rays falling on this lens, after refraction, they converge to a point. Such a lens is known as converging lens. So in general, we can define converging lenses as the lenses in which the rays falling on the lenses after refraction, they converge to a point on the principal axis. And let us take double concave lens. It will also have the principal axis, which passes through the centers of the curved surfaces, and the center of the lens is known as optic center. A ray passing parallel to the principal axis is incident on the concave lens, and after refraction it bends away from the principal axis, so it will never meet the principal axis. Such a lens is known as diverging lens. So in diverging lenses, the rays after refraction travel away from the principal axis. Refraction in a convex lens. Let us consider a double convex lens made of glass. On the principal axis, O is a point. From this point, a ray is incident on the left curved surface of this lens. The ray is passing from air to glass, that is from rarer medium to denser medium. Now let us draw the normal at this point of contact, point of incidence. Then after refraction it bends towards the normal. So the ray bends towards the normal and the ray passes in the lens, and it will be incident on the second curved surface, that is right curved surface. Now emerges into air. At the same second curved surface, it is traveling from denser medium to rarer medium. So it bends away from the normal. By drawing the normal at this point, we notice that it is bending away from the normal. Then this ray, the emergent ray, will meet the principal axis at I. So I is the position of the image of the point object at O. This is how the refraction takes place in a lens, in a convex lens. We can draw a similar figure for the refraction in a concave lens. Let us summarize the refraction in convex lens. The ray starting from O, it is falling on the left curved surface and it is traveling from rarer medium to denser medium, so it bends towards the normal. Inside the lens it is traveling and it is incident on the second curved surface. At the second curved surface it is traveling from denser medium to rarer medium, hence it bends away from the normal, so it travels towards the principal axis and meets the principal axis at I. So I is the image point of the point object O. Lens maker's formula. Before we understand this formula, first let us go through the construction of the lens. We know that the lens is bounded by two curved surfaces. Let us take double convex lens. Here the left side curved surface is having a part of one spherical surface, and the right side curved surface is the part of another sphere. The radius of curvature of the right side curved surface is R1 and the radius of curvature of the left side curved surface is R2. So whenever we say the radii of curvature, we have to recollect this figure. Now if the material is of refractive index mu, then the focal length of the lens is given by the relation 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. This is known as lens maker's formula. That means for making a lens, if you know the radii of curvature and the refractive index of the medium, you can say the focal length of the lens prepared. So this formula helps us in finding the focal length of the lens. While using the lenses, we use certain sign conventions. Let us take one of the sign conventions. The sign convention which we are going to adopt is distances are measured from the optic center of the lens. Distances are measured from the optic center of the lens. Distances situated along the direction of the incident ray are taken as positive. Distances situated along the direction of incident ray are taken as positive. Distances situated opposite to the direction of incident ray are taken as negative. The lens formula is, that is, the relation between focal length, object distance and image distance is given by 1 by f is equal to 1 by u plus 1 by v. The relation is 1 by f is equal to 1 by u plus 1 by v. For applying this relation, the sign convention adopted is f is taken positive for convex lens and a negative for concave lens. F is taken positive for convex lens and f is considered negative for concave lens. U is positive for real objects and U is negative for virtual objects. U is taken as positive for real objects and it is taken as negative for virtual objects. V is positive for real images. For real images, V is positive and V is negative for virtual images. Refraction at a curved surface. Refraction at a curved surface. Consider the curved surface APB. O is a point object on the principal axis. OA is the ray incident at A on the curved surface. C is center of curved surface and CA becomes the normal to the curved surface at A. So, the angle between the incident ray and the normal is angle of incidence. Suppose to the right of this curved surface, the medium is a denser medium. Then the ray gets refracted towards the normal. Let AI be the refracted ray in the second medium. Then the angle between the normal AC and the refracted ray AI is the angle of refraction R. I is the point image of the point object O. Now, P is pole of the curved surface and PO is object distance U. PC is radius of curvature R. Pi is image distance V. Now, our aim is to apply the sign convention in lens maker's formula. Here, from the center of curved surface P, the distances to the right are positive because they are in the direction of incident ray, and the distances to the left are negative because the distances are opposite to the direction of incident ray. The distances to the right will be positive and to the left will be negative, according to lens maker's formula sign convention. Here, V and R become positive and U becomes negative. U is negative and V and R are positive. Summary of the class. A ray passing through different media undergoes deviation at the interface of the two media. If the ray travels from rarer medium to denser medium, it bends towards the normal. If it travels from denser medium to rarer medium, it bends away from the normal. For a pair of media, sin I by sin R is constant. This is known as Snell's law. Generally, we take I in air and R in the medium, and we call this ratio as refractive index of the medium and represent it by mu. When the light ray travels from denser medium to rarer medium, for a particular angle of incidence C, the ray grazes along the surface of separation of the two media. Such an angle is called critical angle. If the ray is incident at an angle greater than critical angle in the denser medium, then it undergoes reflection into the denser medium. It is called total internal reflection. Then optical fiber works on the principle of total internal reflection. In this, communication is very quick because here the communicating medium is the light ray. The communication is done by light ray, hence it has got the highest speed, so the communication becomes very quick and easy. A medium, a transparent medium bounded by curved surface is known as a lens. Lenses are they are classified into converging lens and diverging lens. And the refraction takes place at both the curved surfaces, and thereby images will be formed by the lenses.